Let's take a look at some applications of first derivatives. Optimization is one of the primary applications that you'll see in math classes and in the real world. So imagine that we have a 100-foot of fence. This is a very simple example. I've seen it in many different college and high school courses. You have 100 feet of fence to make a rectangular play area, or whatever, it doesn't have to be a play area, alongside the wall of your house. Right, the wall bounds one side. What's the largest possible play area? Or it could be a cow pasture or garden or whatever. So we have three sides made up by that fence. It's 100 feet long, and then the other side is the house. And so we know that if it's a rectangle, we have right angles here, and these values are equal. So we've got x and x, and then this one is 100 feet minus whatever these two are, which is 2x. And so how do we find the largest possible area there? Well, we know that our area function is equal to x times 100 minus 2x, and we'll carry out the distributive property there. We get 100x minus 2x squared. Right, so there's our area function, and then that function primed, or that function, the first derivative of that function, excuse me, is 100 minus 4x. And remember from a previous video when we were talking about the first derivative test, we know that we're looking for a maximum, right? We're looking for a maximum, and so this is just an application of the first derivative test. Therefore, we set this equal to 0, so 100 minus 4x is equal to 0. We get 4x equals 100, or solved simply, x equals 25. All right, and so we're going to take that 25 value, we're going to plug it back into the original equation, and we get a is equal to 100 times 25. 100 times 25 minus 2 times 25 squared. 100 times 25 is 2500. 25 squared is 625, times 2 is 1250. And here's our answer. 2500 minus 1250 is 1250, and then don't forget our units, square feet. Okay, another example of optimization, right? Finding a maximum. Marketing tells you, can't see that. Okay, marketing tells you you're in a business, and the marketing department tells you that if you set a price of an item at $10 and you'll be unable to sell it, so you'll have 0 sales, but that you can sell 500 items for each dollar below $10 that you set the price. Suppose your total fixed costs are $3,000 and your marginal cost is $2 per item. What's the most profit you can make? Well, so we're going to have to come up with a couple of different functions. First, our profit function. Profit as a function of x, and x is in price. Profit is nx, the number sold, times the price, minus 3,000, minus $2 per item, and that's the number sold. Okay, but what is n? So we have to find n. Right, how do we do that? Well, next problem here, n is equal to, we're going to start with 500, and we said, marketing said that we were going to sell 500 for every dollar below $10, and then just because it's every single dollar, if we had, if every 50 cents, I would put a 0.5 down here. But anyway, we're going to sell 500 of these items for $10 minus whatever that price is there. And then again divided by 1. And again, if it said below, every $2 below, or every 10 cents, we would put that number down here. So we don't need to say that. But in case you see another problem similar, you put the value less than whatever this is down here. Okay, so we got n. So we've got a single variable for our profit function. Let's write it out over here. Profit as a function of price is equal to 500 times 10 minus x times x minus 3,000 minus 2 times 500 times 10 minus x. Okay, we'll do some algebra. We come up with negative 500x squared plus 6,000x minus 13,000. And we're going to set that equal to 0. Oops, sorry, excuse me, we're not going to set it to equal to 0 yet. And take p prime of x, first derivative. Remember, this is our profit function. In order to find the local minima or maxima, we need to take the first derivative, find those critical points, and then take that critical point and plug it back into the original equation. Right? So our first derivative, we'll take this 2, drop it down, use the power rule. 2 times negative 500 is negative 1,000. This x stays, and then we're going to add to that 6,000. We'll drop our first order variable here, and then our constants are eliminated. So we get p of x equals negative 1,000, x minus 6,000, set that equal to 0 in order to find our critical point. And we'll take this negative 1,000x, put it on the other side. We get 6,000 equals 1,000x. Therefore, x is equal to 6. Pretty simple. And remember, this is $6. That's our price. Okay. So at $6, that's where we think, or we've calculated, our maximum profit will be. So we'll plug this 6 back into the original profit equation. You get negative 500 times 6 squared, or 36. Plus 6,000 times 6 minus 13,000, and we're working in dollars here, and this is all equal to $5,000. So that is our maximum profit given that product. Okay, let's take a look at another example here. This one's a little bit more complicated. The strength of a rectangular beam is proportional to the product of its width, W, times the square of its depth, D. Find the dimensions of the strongest beam that can be cut from a cylindrical log of radius R. Okay, and so we've got W and D. We've also got another dimension here, which is R. Be important for us, R and R. Right? D is equal to 2R. Let's take a look at what relationships we know. We know the strength, or S, is equal to the width times d squared. And we can also use the Pythagorean Theorem in here. So we've got W squared plus d squared is equal to 2R quantity squared, or 4R squared. Okay. In order to illustrate a point, I'm just going to come up with an arbitrary number for R right now. And let's solve it without R as a variable, or R as a letter. And the number that I've come up with is 16, and so we'll say that W squared plus D squared is equal to 4 times 16, or 64. Okay, so W squared plus D squared is equal to 64, therefore D squared is equal to 64 minus W squared. Right, and let's plug that back into the strength equation. So S is equal to W times 64 minus W squared. We'll carry out the distributive property here. We get 64 W minus W cubed is our strength equation. We'll take the first derivative of that. Let's call that S primed. And we get 64. Our first order variable disappears, bring down that power here, turn it into a coefficient, reduce the power by 1, and then we're going to set this equal to 0. Excuse me. Solve for W by setting it equal to 0, yes. Alright, so we get 64 is equal to 3W squared. We'll divide by 3 on both sides. We get W squared is equal to 64 over 3. And then to find W, we're going to take the square root, 64 over 3, or 8 over root 3. Okay, and that's not incredibly important right now. Remember that R is equal to 4. So now let's take this here and put it back in terms of r. So w is equal to 2 times r over root 3. And then we can easily find d from that. I did this just to illustrate a point. Now let's go back and work this in with r as a letter. So we've got w squared plus d squared is equal to 4r squared, and then d squared is equal to 4r squared minus w squared. So our strength equation then is w times 4r squared minus w squared. And we'll distribute that w. S is equal to 4r squared w minus w cubed. Now when we take the first derivative, in order to come up with the right answer, we have to recall that r is actually a constant. R is not a variable like w and d. We have to keep this r as a constant, right? So we're going to drop this. We get 4r squared, and that's minus 3w squared. Solve, set is equal to 0. Solve for w, excuse me. We get 4r squared is equal to 3w squared. Divide by 3. 4 thirds r squared equals w squared. And then take the square root. We get w is equal to square root of 4r squared over 3. Simplify. We get 2r on top and root 3 on the bottom. And then some teachers will make you say something like 2r root 3 over 3. Just multiply by root 3 over root 3. Right? Not always the most important thing, but some teachers will require that. Okay, so we got the same answer here, right? And we can easily solve for d. We've got d squared. D squared is equal to 12 minus 4 r squared over 3, which is equal to 8r squared over 3. We'll take the square root and we get d is equal to 2r root 2 over root 3, right? So again, this is related to the first integral test, where in order to optimize or find the maximum, what we have to do is find the maximum of the function, and we know that if we take the first derivative, set that equal to 0, we'll come out with critical points. One of them will be a maximum, one of them will be a minimum. Coincidentally, all of these problems had only maximum. And so we'll take that critical point, plug it back into the original equation, and we get our answer.